NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve logarithmic equations by converting them to exponential form. We'll use the key rule, log base a of f of x equals b if and only if f of x equals a to the power b. We'll apply it to several quick examples and check domains. Before using the rule, remember the conditions. The base must be positive and not equal to 1, and the argument of the logarithm f of x must be strictly positive. Example, we will solve the logarithmic equation. Log base 3 of x equals 1/2 plus log base 9 of the quantity 4x plus 15. We will then follow the exact algebraic steps one by one, checking the domain and selecting the valid solution at the end. Step 1. Domain. The arguments of logarithms must be positive, so x is greater than 0, and 4x plus 15 is greater than 0, which implies x is greater than negative 15 over 4. The intersection is simply x greater than 0. Step 2. Change of base to rewrite the base 9 logarithm as base 3 squared. Therefore, log base 3 of x equals 1/2 plus log base 3 to the power 2 of the quantity 4x plus 15. Using the change of base rule, this equals 1/2 plus 1/2 times log base 3 of the quantity 4x plus 15. Step 3. Multiply the entire equation by 2 to clear the halves. We get 2 times log base 3 of x equals 1 plus log base 3 of the quantity 4x plus 15. Step 4. Move the logarithm on the right to the left side. 2 log base 3 of x minus log base 3 of the quantity 4x plus 15 equals 1. Step 5. Apply the power rule. 2 times a logarithm equals the log of the square. So we have log base 3 of x squared minus log base 3 of the quantity 4x plus 15 equals 1. Step 6. Apply the quotient rule to combine the difference of logs into a single logarithm. We obtain log base 3 of x squared over the quantity 4x plus 15 equals 1. Step 7. Convert from logarithmic to exponential form. That gives x squared over 4x plus 15 equals 3 to the first power. Step 8. Multiply both sides by the denominator and expand. X squared equals 3 times the quantity 4x plus 15. So x squared equals 12x plus 45. Step 9. Move all terms to one side to form a quadratic equation. X squared minus 12x minus 45 equals 0. Step 10. Factor the trinomial. The factorization is open parenthesis x minus 15 close parenthesis times open parenthesis x plus 3 close parenthesis equals 0. Step 11. Set each factor to 0 for the candidate solutions. Therefore, x equals 15, or x equals negative 3. Step 12. Check the candidates against the domain x greater than 0. Negative 3 is not in the domain, so we discard it. The solution set is D equals the set containing 15. Here is the given equation. We'll simplify constants on both sides first, then use log properties to isolate x. Rewrite each constant using prime bases. 9 equals 3 squared, and 27 equals 3 cubed. 8 equals 2 cubed, and 16 equals 2 to the 4th power. Use the power rule for logarithms. Log base a to the m of b to the n equals n over m times log base o of b. This makes the first constant 3/2 and the second constant 4/3. Now substitute these values back. 2/3 times 3/2 equals 1, so the coefficient of log base 2 of 3 plus x is 1. On the right, 2 divided by 4/3 is 3/2, and 3/2 minus 7/2 equals negative 2. Apply the quotient rule. Log of m minus log of n equals log of m over n. Convert from logarithmic to exponential form. Log base 2 of something equals negative 2 means the something equals 2 to the negative 2, which is 1/4. Cross-multiply to solve for x. For times the numerator equals the denominator. Finally, check the domain. Each logarithm requires a positive argument, 3 plus x greater than 0 and 7x plus 9 greater than 0. With x equals 1, both are positive, so the solution is valid. Therefore, the solution set is the singleton one. In this lesson, we will solve a logarithmic system with an absolute value following a clear, case-based algorithm. First, here is the problem statement. Step 1. Establish the domain. For any logarithm to be defined, its argument must be strictly positive. Therefore, both x plus y and x minus y must be greater than 0. Also, because x minus y is positive and the product x y equals 3 is positive, it follows that x and y are both positive and x is greater than y. Step 2. Split the equation using the absolute value definition. Case 1. Log base 2 of x minus y is greater than or equal to 0. Then the absolute value does nothing, and we simply add the logarithms. Case 2. Log base 2 of x minus y is less than 0. Then the absolute value flips the sign, and we subtract logarithms. Let us work through case 1. Adding logarithms gives the product rule. So log base 2 of x plus log base 2 of x minus y equals 3 becomes log base 2 of the product x plus y times x minus y equals 3. And log base 2 of x minus y at least 0 means x minus y is at least 1. Converting the logarithmic equation to exponential form gives x plus y times x minus y equals 2 to the third, which is 8. We now combine the relations with x, y equals 3. Using the identity x plus y times x minus y equals x squared minus y squared, we get x squared minus y squared equals 8. Substitute y equals 3 over x from the product x, y equals 3. Then x squared minus 9 over x squared equals 8. Multiply by x squared and rearrange to obtain the quadratic x to the fourth minus 8x squared minus 9 equals 0, which factors into x squared minus 9 times x squared plus 1 equals 0. The positive root consistent with x greater than y greater than 0 is x equals 3, and then y equals 1. Check the condition x minus y at least 1. 3 minus 1 equals 2, which satisfies it. Now case 2. Since log base 2 of x minus y is negative, we have 0 less than x minus y less than 1. Using the quotient rule, the equation becomes log base 2 of the fraction x plus y over x minus y equals 3, which implies x plus y equals 8 times x minus y. Combine 9, y equals 7x, with x y equals 3. From the linear relation, y equals 7/9 x. Substituting into x, y equals 3 gives 7/9 x squared equals 3. So 7x squared equals 27, and x squared equals 27 over 7. Taking the positive root yields x equals 3 root 3 over root 7. Using x, y equals 3, y equals 3 over x, which simplifies to root 7 over root 3. Finally, verify the bound 0 less than x minus y less than 1. The difference equals 2 over root 21, which is about 0.436, so the bound holds. We have found both valid solutions and verified all conditions. The solution set is the ordered pair 3, 1, and the ordered pair 3 root 3 over root 7, root 7 over root 3. In this lesson, we solve a parameterized logarithmic equation. We will find for which values of the parameter of the equation has solutions for x, and what those solutions are. Step 1. Determine the domain. For a logarithm, the argument must be positive. So, 2x minus x squared must be greater than 0, and 1 minus x squared over 2 must be greater than 0. Solving gives 0 less than x less than 2, and the absolute value of x less than square root 2. Their intersection is 0 less than x less than square root 2. Let's picture that on a number line. Step 2. Sign of the logarithms on this domain. Notice that 2x minus x squared equals 1 minus the quantity 1 minus x squared. So it is less than or equal to 1. And 1 minus x squared over 2 is also less than or equal to 1. Because the bases 3 and 11 are greater than 1, both logarithms are less than or equal to 0 for all x in the domain. Step 3. Compare the two sides. Each coefficient 1 plus something squared is at least 1. If it is not negative 2 and is not 1/3, then both coefficients are strictly greater than 1. Multiplying a non-positive logarithm by a number greater than 1 makes it even smaller, so the left side is less than or equal to the right side, and equality can happen only when both logarithms are 0. Solving those two conditions, 2x minus x squared equals 1 gives x equals 1, and 1 minus x squared over 2 equals 1 gives x equals 0. They cannot hold simultaneously, so there is no solution when it is not -2 and not 1/3. Now consider the special case at equals -2. The first coefficient becomes 1, and the second becomes 50. The equation reduces to 49 times log base 11 of 1 minus x squared over 2 equals 0. So the logarithm is 0, which gives x equals 0. That is not in the domain 0 to square root 2 open at 0. So this case has no solution. Finally, consider it equals 1/3. Now the second coefficient is 1, and the first equals 58/9. Subtracting the common terms yields 49/9 times log base 3 of 2x minus x squared equals 0. So the logarithm is 0. That gives 2x minus x squared equals 1, and therefore x equals 1. This lies in the domain, so this case provides a unique solution. To summarize, the equation has exactly one solution, x equals 1, when it equals 1/3, and no solution for any other value of a, including a equals -2. The system is x to the power log y equals 1,000, and x times y equals 1,000,000. Our goal is to follow a clear chain of algebraic steps to arrive at exact solutions for x and y. First, we take the base 10 logarithm of the first equation. Log of x to the power log y equals log of 1,000. Using the power rule, the exponent log y comes down, and we write 1,000 as 10 to the 3. Therefore, log y times log x equals 3. Next, we take the base 10 logarithm of the second equation. Log of x, y equals log of 1,000,000. Apply the product rule, log x plus log y, and write 1,000,000 as 10 to the 6. We conclude that log x plus log y equals 6. To make the algebra transparent, we introduce substitutions. Let it equal log x and b equal log y. Then our system becomes a times b equals 3 and a plus b equals 6. Solve the system by substitution. From a plus b equals 6, b equals 6 minus a. Substitute into a times b equals 3 to get parenthesis 6 minus a parenthesis times equals 3. Expanding gives 6 a minus a squared equals 3. Rearranging, a squared minus 6, a plus 3 equals 0. Use the quadratic formula with a equals 1, b equals -6, and c equals 3. A equals 6 plus or minus the square root of 36 minus 4 times 1 times 3, all over 2. The discriminant simplifies to 24. Square root of 24 is 2 times square root of 6. Divide numerator and denominator by 2 to get a equals 3 plus or minus square root of 6. Now compute the corresponding values of b, and then back substitute to x and y. If it equals 3 plus root 6, then b equals 6 minus a, which is 3 minus root 6. Since it equals log x and b equals log y, we get x equals 10 to the power a, and y equals 10 to the power bx equals 10 to the power 3 plus root 6, and y equals 10 to the power 3 minus root 6. If it equals 3 minus root 6, then b equals 3 plus root 6. Therefore, x equals 10 to the power 3 minus root 6, and y equals 10 to the power 3 plus root 6. Both ordered pairs satisfy the original system. These are our final solutions. In this example, we will follow a precise, step-by-step algebraic pathway to find the parameter n. First, the problem statement. Step 1. Take the logarithm base 2 of both sides. Using the log of a power rule, the exponent will come down as a factor. Step 2. Apply the power rule explicitly. Step 3. Simplify log base 2 of x cubed to 3 times log base 2 of x, and then substitute t equals log base 2 of x. Step 4. Replace log base 2 of x by t. Then expand to obtain a quadratic in t. Step 5. Here, the product of the roots equals c over a, which is negative log base 2 of 13 over 3, a negative number. Therefore, the quadratic has 2 real roots with opposite signs. Step 6. Since t equals log base 2 of x, each t root maps to an x root by x equals 2 to the t. Step 7. Multiply the x roots. Using exponent rules, the product is 2 to the alpha plus beta. But the problem states the product of the real x solutions equals 32. Step 8. Equate the two expressions for the product. 32 equals 2 to the alpha plus beta, so alpha plus beta equals 5. Step 9. Use Vieta's formula for the sum of the t roots. 4 3t squared minus n t minus log 2 of 13 equals 0. The sum equals negative b over a, which is n over 3. Step 10. Set the two expressions for alpha plus beta equal and solve for n. Therefore, the required parameter is n equals 15. We followed the exact structure. Logarithm, substitution to form a quadratic, mapping back to x using the given product 32, and Vieta's formulas. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.